Okay, welcome back. This is week 2 of 2021-2022 SEM 2. Today is 21st of January. We're continuing our discussions of systems, the O2B slides. Now, let's see the slides first. The O2B system slides is here. And we're going to give a whirlwind tour of these few slides. Right. So what's a system? Basically, if I have the input here and I have the output here, so this is a system. And sometimes you write the system this way, f of x, and then you see the input is x, and the output is y. And then we are to describe this relationship f, typically by an equation in your high school days. But today we are doing it a little bit differently. We want to have a discrete time system. So the input is n, meaning that I have a sequence of numbers x of n, and the output is also y of n. And then, of course, how is this system described is later on you'll see. Now, typically we give a letter to the system, and which is h, and you'll figure out why later on as well. All right. Now, when we have a system, of course, this is the equation describing the system. And different equations will make the system behave differently. So what is the characteristics of a system that we're interested in? And you hear the word LTI a lot. The word L here stands for linear. We hope that the system is linear and time invariant. Now, why are we discussing all this? Is first, in the next few minutes, I'm going to discuss all these characteristics, linear, time invariant, and so on. And where did this appear in your tutorial one? In your tutorial one, let's open up the questions. In your tutorial one, from question 5 onwards, it will begin to ask you, I have an equation y is described by some function of x. So I have 3 of them. And it asks you, is the system linear? Then after that, it asks you, is the system time invariant? So again, you're given output and input and some equations, and you have to figure out whether the system is linear and time invariant or not. After you have figured out this, then you realize that in our course, we only deal with system that is linear and time invariant. All right. Other than linear and time invariant, we're interested in that the system that we are playing with must be stable. So here is BIBO stable. BIBO stand for bounded input. Oops. And the BO stand for bounded output. Right. So where input means x of n never exceeds a certain value. And the output y of n also does not go to infinity. So when the input is bounded, the output is bounded. Now, of course, if you say, if the input is not bounded, for example, if I send an infinity, then it doesn't matter. We're not interested in that problem. What we're interested in is that when we send an input that's bounded, would the output be bounded? And we want to design system like that because this is a stable system. That means it doesn't, create problems later on. Right. Okay. So later on, you'll realize that I'll talk about something called impulse response in question 8. And that's also an important thing, but we'll come. Okay, I'll show you what the impulse response mean now. Among all the input that I can send, this is the most interesting one. And what does it look like to you guys? -1, -2. Yep, can you type? Yeah, what do you think this signal is? So the equation defining this signal is delta n, the impulse. The amplitude is 1, and at time index 0, it is 1. At every other value, it is 0. So this is an impulse. When I send an impulse to a system, the output has a name. It's called the impulse response. And the impulse response is typically a sequence of number described by the letter H, and it is the same H here. So you'll realize that we describe a system by the impulse response. We'll send an impulse, and if this is a linear time invariant system, whatever comes out is the impulse response is the important sequence, because with the impulse response, we can do everything else, which is calculating output for different inputs. All right, so you realize that tutorial 1 is doing nothing but telling you all these important words. Okay, what are the important word? A causal. Okay, let us see. So I haven't tell you all these terms yet. So I'm going to list down first, and then I'll tell you. So I'm going to tell you what a causal is, as well as what is a relaxed system. We have all these names now: linear, time invariant, stable, causal, and relaxed. So we're going to go through all this terminology one by one. All right, let's do the most important one first, which is linear. Now, the linear systems look like this. Let's call this H. And if we have x1 of n, and let's pretend we can get y1 of n. Okay, so x1 of n is a sequence of numbers, whatever sequence, and y1 of n is whatever is being produced by H. Now, a linear system needs homogeneity, means scaling. What does it mean? Means if I multiply this sequence by alpha, the output is multiplied by alpha. Okay, so homogeneity means that. So if alpha is equals to 0, the whole sequence is 0, the output is a sequence of 0. What other things I need? Well, let's assume we can send x2 of n, the same H, okay, the same system. And let's call the output y2 of n. We don't care what x2 and x1 is now, it's just some. Okay, can you mute yourself, please? Okay. Now, what I'm going to do is this. I'm going to try to so again, homogeneity means if I multiply the x2 by beta, the output is also multiplied by beta. Now the second property is the additive property, meaning that if x3 of n is equals to alpha x1 of n plus beta x2 of n, then what is y3 of n? And the answer is it must be equals to alpha y1 of n plus beta y2 of n. So if this property holds, then we say that the system is linear. If this property does not hold, then this system is not linear. Okay, right. Now, why is linearity so important, guys? And let's now just look at this. Okay, let's look at this problem. Let's have a very simple alpha. How about this guy? This is 0 and this is 1. And beta, second x2 is this. 0, 1, 2, maybe just here. Maybe this is 2. Then what you realize is that we are saying that x3 is equals to, at time 0, 1. At time 1, nothing. At time 2, 2. At time 3, nothing. At time 4, nothing. So what you are saying is that we can break a complex sequence into very simple sequence. Just one impulse scale. And I can do this infinitely. I can break down this guy. Okay, later on you'll see why we want to do that. But because only when the system is linear, we can do this, breaking down the input, and we will know that the output can be summed. So this is a critical fact. All right, the other thing which must have make this equation or this system useful is something called time invariance. Now, remember that the most important input is the impulse. So if I send an impulse and the rest is 0, of course, what is yn? And I told you that whatever sequence that comes out is called the impulse response. It is a sequence of numbers. Let's just, for fun of it, just pretend that I have a system that does this. 1, 2, and 3, and nothing else. So what is Hn? You can write it this way. And then you have to add that little arrow here to say n is equals to 0. So this is Hn, defined as a sequence of numbers. This is Hn in a stem plot. This is Xn, the delta n. All right, now, what is time invariance, guys? The time invariance means that the system will respond and it will not change. His response behavior does not change with time. So what do you think should happen when I send the same input, but now it is delayed by k? Guys, can you help me? This is k plus 1. This is k plus 2, and so on. And this is still 1. So nothing else I send. To the same system H, what should I get, guys? If the system is time invariance, it means that the system's response does not change with time. So if I delay my input, the output will be delayed. So what is Yn? It is nothing but h of n minus k. What does h of n minus k means? What is h of n? H of n is this guy on here. H of n minus k means a delayed version of h of n, because my input x of n has been delayed by n minus k. Or I should say my input has been delayed by k sample. The output, if it's delayed by k sample, means that the system is time invariant. time does not matter. The behavior of the system is invariant to time. And therefore, what do you think it should be? And it'll be 0 here, 0 here, 0 here, until k. At the k value, we basically look at our original response and copy it here. So what should the response be? The response would be, at k would be 1, 2, 3. This is y of n. And isn't y of n equals to h of n minus k? If this is h of n, the same thing. K plus 1 here, k plus 2 here. You look at the green guy, it is nothing but a delayed version of these 3 lines. This is just an example to tell you that my h is these 3 lines. Okay, that's all. All right, so now we understand linear and time invariance now. Okay, so when a system is linear and time invariance, something very useful will come out. Okay, let us see what's so useful about this. All right. Now, let us assume that my input is 1 as well as maybe 2, okay? And 1 and nothing else, okay? All right, so I'm going to now find output yn, given this is my input, and given that h of n is equals to the sequence, this is n equals to 0, what I've said. And then how do you think? And I tell you that my system is linear and time invariant. So what you should do is that, the system is linear. What do? I take 2 and I substitute nothing else. I take 1 and I have 0 everywhere else. This guy plus this guy is the input. Okay, so I just break my not very complicated. It's just two little stem plot into 2 parts. But these 2 parts is very interesting. This is nothing but delta of n minus 1, the impulse that is delayed. What is this guy? This is 2 times delta n, the impulse that is doubled. Okay, we can decompose this signal into this and this. We make use of the idea that the system is linear and time invariant. Okay, let's make it time invariant first. If it is time invariant, what do you think the output should be for this guy? Okay, we said time invariance means that the output should be 1, 2, 3. And since I delay my input by 1, my output will be delayed by 1 because this is the impulse. So my output should be, let me draw for you, 0, 1, 2, 3. It'll be 1, 2, and 3, and nothing else. What is this? This is h of n minus 1, right? It is exactly what is, we remember what is hn? We plot this, this is hn minus 1. What about this guy? Remember, I can send my impulse and I'll get exactly 1, 2, 3. But since I scale my input by 2 and the system is linear, it uses the homogeneity principle. So 2 will multiply by the sequence 1, 2, 3. Therefore, this guy will be, let me get this right, 0, 1, 2, 3, 4. And at time 0, it'll be 2. At time 1, it will be 4. And at time 2, it will be 6 and nothing else. Now, isn't this 2h of n, right? So I have 2h of n, I have 1h of n minus 1. Now, let's remember what is. So what is the output, guys? The output, because the system is linear, is nothing but this guy, 2h of n plus 1h of n minus 1. So the output is 2h of n plus 1h of n minus 1. And plus nothing else, because there is no other input. So I just throw this away. Now, let us see what is x2 and 1. What is the 2? The 2 is actually x0, the value of the input at time index n equals to 0, or let's call this k equals to 0. This guy is x of 1. If you generalize this, you realize that the output is equals to x0 h of n minus 0 plus x of 1 h of n minus 1. Later on, you realize why I put all this. And then if you want to generalize this, h of n minus 2. And then if you have previous values before, it will be x of minus 1 h of n plus 1 and so on. The equation will be reduced to this equation called x of k h of n minus k. K equals to negative infinity to positive infinity. And this is the output yn. And this equation here, you must memorize and derive from first principle, and it is called the convolution equation. Right, so in about 20 minutes, we derive from first principle the convolution equation only by understanding the word linear, time invariant, using these two properties, and we get this equation. So what's so cool about this is that from now on, once you know the input, once you know h of n, you can derive y of n. So that is why the h of n is the most you need from a linear time invariant system, because once you have h of n, you can now compute for any input. Okay, so I will now let you see the whole picture again from here to here, and then I hope you understand. Okay, I'll pause now. Now, relax. When we say that a system is relaxed, means when input is a sequence of zeros, there is no input basically, then the output is a sequence of 0. Okay, so we say that the system is relaxed means the output is 0. Nothing is happening. There's no input, or the input is zeros and the output is 0. What about causal? Now, you realize that something is going on here for this part. H of n minus k, when k equals to 0, then this is h of 0. When k equals to 1, we have h of n minus 1, meaning a delayed version. A delayed version of hn. So h of n minus 2, we still understand. So 2 sample delay. What about h of n plus 1? Then let's draw h of n plus 1. At time 0, this is 1, this is 2, this is 3. For h of n plus 1, given that this is 1, 2, 3, and h of n is our little example here. Now, what just happened? It basically moves the whole hn left side so that the time of the sequence starts from -1 now. Now, you look carefully at the equation. Summation of x of k, h of n minus k. K equals to negative infinity to infinity. What is this value? This is h of -1. This is h of 0. This is h of 1. To get this value, then we need k to be plus 1. Okay, so something is happening here. All right, we need h of n minus k to shift left. Now, what it means is that we will need future values of k to perform this. And when this happens, then we say that the system is not causal. Right? Maybe I should say, if I have a hn that looks like this, -1, 0, 1. Sorry, I take it back. I say my impulse response must look like this. Means that before time 0, values exist. When this happens, then you will realize that I need future value of x to evaluate h of n minus k. And when this happens, then we looking ahead of the input to evaluate the convolution equation. In real systems, we only have past values to evaluate for future value. So in real systems, the system is causal. But if you have a recording of a voice, if you have a recording of an image, of course, you can see future value. Because if you're listening to the speech now, you already know what I'm going to say in the future because all the recordings are given to you. So for some application, it is possible to look at future value, but for real-time system, it is not. Okay, so this is what we mean by causal. When the impulse response exists on the left-hand side of time index 0, then the system is not causal. So these are some of the things that you need to understand. All right. Now, the last thing that we want to discuss is called Bibo stable. Bibo stable means when the input is bounded. What does input bounded means? Now, I'm going to give you an input. Zero, -1, 2, 3. So the question is x of n equals to u of n, the unit step? Is this bounded? So this is the tutorial question. And the answer is yes. X of n only have maximum value of 1. It is bounded by 1. The value doesn't go up above 1. What about this value, guys? So this was our h of n. It was 1, 2, and 3. Is this bounded? Yes, because h of n never exceeds 3. What about this guy? 2 to the power of n. So this is 1, this is 2, this is 4, this is 8, and so on. The sequence to the power of n. Is this bounded? Of course not. So this is not an unbounded sequence. We are only studying the case when the input is bounded, and we want to see whether the output is bounded or not. And if it is, then we call the system bounded input, bounded output stable. It is stable. We want to design systems that are stable. All right. Without telling you the proof, I will now give the criteria. Again, you look at the system, and the system, if you have the impulse response, you take the impulse response and you sum it absolutely. And if this value is less than infinity, then the system is bounded. Sorry, is Bibo stable. Okay. So again, h of n appears. H of n describes the system. All I need to do to study whether the system is bounded, is Bibo stable, is to take the absolute value of the sequence, sum it, and then check. If it is less than infinity, then the system is bounded. So what about this guy? So h of n is 1, 2, 3, followed by all zeros. Then of course it's trivial because it is nothing but 1 plus 2 plus 3. The answer is 6, right? Even though it goes up, but the rest of the value is 0 up to infinity. Therefore, a finite sequence is always, when we sum it, is always less than infinity. Therefore, when an impulse response is finite sequence in nature, then the system immediately is stable. What about these guys? Zero, 1, 2, 3, and so on. The sequence h of n is equals to half of n. So as n goes to infinity, half of n becomes very, very small. The question is, if I have an impulse response that looks like this, is this stable or not? So now you go back and study your first year math and then check whether this geometric series is absolutely summable or not. If it is, then the system is stable. If it is not, then the system is unstable. Okay, so I have spent about 35 minutes now to talk about the properties of this H. We have talked about linear, time invariant, causal, relax, and stability. Okay, I'll pause now and take questions. So the student asks, how to prove stability, and the answer is in page 29 of your slide here. The derivation comes from the convolution equation. The output is the input convolved with Hn. This is the convolution operation, that little star sign. It is nothing but the same equation that I wrote, this one. Now, when the x is bounded, meaning that absolute value of x is less than some b, some very big b, but it's not infinity, then what we realize is that the trick is we assume all x is this very, very large value. Now, what we are then multiplying is with respect to the impulse response delayed. And then if you work out the sum, you realize that it is the largest value that you can ever achieve is the largest value of b, of x, multiplying the absolute value of the impulse response. And therefore now, if b is finite, therefore whether output is finite or not depends only on this little guy here. And therefore, when h of k is absolutely summable, then our system is Bibo stable. So that is the proof.
Oh, okay.
So now I will talk about the next important big idea called the eigenfunction of LTI system. Now, let's recap what we know. I send delta n, the smallest, the simplest, but the most important sequence, which is 1 at time 0 and at nothing else, 0 at any other value. And this is the LTI system. And then by now, you know that it is output equals to sum of xk, which is the input, h of n minus k, the convolution equation. And this is x of n. Now, if you are lazy to write this equation, you can write it in this form. This operator is the same as this above equation over here. Now, guys, when you perform convolution with an impulse, what do you get? When you perform convolution and impulse, you realize that you substitute into this equation, the only thing that is going to happen is out comes the impulse response. Okay, so if you do not believe me, by brute force, you solve this equation. K, where is K happening? Only here. Only when K equals to 0, is this 1. The rest of the values are 0. So only x of 0 will get h of n. See, everything else drops out. So this is the cool idea. So when you convolve with an impulse, you get h of n. What about when you convolve with a delayed impulse? So now, delta of n minus 2, right? Then the interesting thing comes only when at delta n minus 2. So only when, basically when x of 2 means here. X of 2 means h of n minus 2. What is h of n minus 2? A delayed version of h of n by 2 samples. So you must understand this intuitively and with, and therefore the math becomes trivial. All right. Now, let me ask you now. Let's still play with that 1, 2, 3, okay? Just for the fun of it. 0, 1, 2, 1, 2, 3. I send an impulse and I get h of n. I get y of n to look like this. I send an impulse, I get 1, 2, 3. The question to you is, this is an impulse response, but the output looks nothing like the input. Okay? So, but there are special functions. There are special functions that when I have x of n equals to an eigenfunction, and I don't tell you what is this first, but you can guess very soon, then actually it is the same function, scale, and phase shift. So there are functions that when you pass through an LTI system, it will be scaled and phase shifted. What are the functions do you think are these? And you realize sine omega n, cosine omega n, exponential j omega n are an eigenfunction. If you send a sine in, out comes a sine of the same frequency, but phase shifted. So you have A, for example, this is 1, you'll become A. Whatever A is, I have no idea. And alpha. You send 1, you become B, for example, cosine plus beta. And if you have 1, you become C. Can you see now? So this is what we are saying. Sine, cosine, and complex exponential are eigenfunctions of LTI. LTI systems will only change the amplitude and introduce a phase, whether it is positive phase delay or negative phase delay later on. All right, so I'm going to show you now. And in fact, this is a tutorial. This is the lab question. Okay, I use MATLAB because I'm just lazy, but the idea is the same. So I first plot, let's just simply plot the impulse. At time 0, I have 1, and at every other time, I have 0. My input is X that looks like this. My H, the impulse response, is that 1, 2, 3 I'm playing with. My output is X convolved with H. So now I will show you X convolved with H. My X is this, my H is this, and my Y is this 1, 2, 3, exactly like what we have in the equation. All right, so CONV is a function that's nothing but convolving X with H. Now, let us now do something else. Let us now generate a X that is a cosine. Okay. And I am going to, so what is X now? X is a sequence of number, 100 points in this example, and it is a cosine with omega 0.1 pi. Now I'm going to plot for you X in blue color and Y in red color. And let us see. X is the blue, which is the cosine with amplitude 1. And my output is the red color one. Okay, don't care about the first cycle first because it's not steady state yet. After a while, it's steady, it repeats itself. What can you tell me about Y? First is the input has been blown up to 5.8. Not only that, it has been phase shifted a little bit. So in the lab, you are supposed to do this and you are supposed to tell me what is the amplitude and what is the phase shift. Of course, it is very hard to calculate, especially when the curve is not so smooth, but we are just approximating. Okay, but if you want to be very, very precise, what should you do? You should use FV2, H1, and FV2 is filter visualization tool. We are sending the impulse response, and now FV2 is a MATLAB package that this little button will show you the impulse response. 1, 2, 3, right? Exactly at time 0, 1, 2. This is the impulse response of the system. The other buttons will tell you the magnitude and the phase response of the output. Let us go to the magnitude first. Click on the magnitude button. Here, the input, this horizontal axis is the frequency of the input signal. Just now, I use 0.1 pi, which is here, 0.1 times pi. The output has a gain of this. Don't look at it in dB. Change, right-click to magnitude. I click this button here, and I see that my output, if my frequency is 0. Well, very close to 1, 0.1, yeah, about here, I guess. Answer is 5.83. Let's look at my plot again. 5.8. Can you see now? So if I change a different signal, for example, now I change it to be 0.3 pi, output is 4.6. Okay, let's go and change 0.3 pi. I change my input to be 0.3 pi. I send 100 points and I will generate my all right. Let's see. My blue guy is my input with sinusoid, sorry, with amplitude 1. My output is here approximately. And the reason why it looks so bad is because it's not smooth. Approximately 4.6. And let's look at the MATLAB again, 4.6. Prof, we are using Python, got difference? Yes. In Python, you have to write your own function to do all this. In MATLAB, we are using this as a calculator to check. Okay, so actually you can write all these functions, the magnitude and the phase shift and things like that. In the exams, that's what we're asking you to do. We're always asking you to plot this 0 to pi. Can show us using Python? Not today. Okay. All right, but you can, I will ask you to use MATLAB and play the word FV2. That's all I'm playing with. Okay. Now, I'm using MATLAB not as a, I'm using MATLAB only as a calculator, right? They have all these functions that I know have been implemented correctly. So I have nothing to do, right? So I'm just, checking whether the magnitude response is good or not. What about the phase response? I should click this button here. The blue line is the magnitude response. The red line is the phase response for every frequency. Okay, so you should use MATLAB FV2 and play with it so that you will check your answers of your tutorials, of your quiz to see that if they are correct or not. You're not here to learn how to use MATLAB. That's not the point. MATLAB has all these functions which you can use to verify your results. That's all. Okay. And of course, you should be using Python to rewrite some of these magnitude and phase, and you can do that as well. Okay. All right, so I will pause now.